Welcome back. We're going to talk a little bit about runtime complexity and compare lists, linked lists, and dictionaries. So let me start by reminding you of the runtime complexity for lists and linked lists. So we had 5 basic operations. Insert, put something into a position. Append, put something at the end of a list. Delete, remove something. Find, that's what we've been talking to for the last few segments of this lecture. Find something in an unsorted list. And random access, give me the nth element. Okay. Now, for lists, the real win here, of course, was access. The random access is very, very fast. And everything else, with the exception of append, because of the way we store lists, is big O of n. Linked lists had sort of the opposite. Insert, append, delete are very, very fast because of the dynamic nature of the linked list. Find is the same, still linear, the same as a list because it's unsorted. And access is where we take the hit because there is no notion of something being stored in a fixed position. You got to follow the links. Right. So let's talk about dictionaries. All right, well, let's see. So first of all, we've already convinced ourselves that find is big O of 1. If the hash function you have is constant time, so it's efficient, it doesn't depend on the size of the list being stored or the table being stored, and it minimizes the number of collisions, so the number of unique key value pairs that will be stored in one entry, then you can find in constant time. That's amazing, amazing, amazing. That's the big win of dictionaries. Insert, append, delete, because of the way we implemented the dictionary as just a bunch of linked lists, is also constant time. So why is that? Well, if I want to insert something, what do? Where do I insert it? Hash it, find the index, add something to the list. In fact, you can add it to the first position because that stuff is not ordered. Append is the same way. Stick it to the end, stick it to the beginning, it doesn't matter. So in fact, insert and append are the same command here. Removal is easy too. Find it, constant time, walk through the key value pairs that are stored there due to the collision, pop one out, that is constant time. So everything here is very, very efficient. And I'll just point out the obvious that there is no notion of random access. There is no give me the 5th element. Dictionaries are unordered. Blue is not in the 3rd position. It's wherever the hash function tells it to. So it's not that access is slow or not slow. There's just no concept of that. Okay? But here you can see the main operations are very, very efficient, thanks in part due to the hash function. So it's a great data structure, particularly good for large databases where you're doing lots and lots of searching for items in the database to find information. Okay, so that's now our 3rd data structure. Lists, variety of linked lists, singly, doubly, circular, sentinel, etc., and now dictionaries, where the big win of the dictionary is being able to find things very, very efficiently. Okay, before we go on to the yet another data structure, which is going to be graphs, I'm going to have you do a drill. So before the next lecture, please carve out a little bit of time. And when I come back, I'm going to give you the drill, and then I'll give you my solution. I'll see you in a few minutes.